Hello, welcome to Lab 1. In Lab 1, we will study the constant velocity motion of the air-powered soccer disc. In this experiment, we will study the motion of the air-powered soccer disc after it has given a push across the table. The soccer disc is actually a small hovercraft. As a result of the airflow, it suffers little frictional forces. And after it has been pushed, the net force acting on the soccer disc is 0 newtons, both in the y direction and in the x direction, that is the direction of the motion. Second law of Newton tells us that there will be no acceleration in this case, and the disc will coast with constant velocity. So, what will be our plan? First, we'll analyze the video with the tracker. And from that, we will calculate the average velocity, and we will extract the xt information to a file. After that, we will make a model of the motion in Python and compare the model with the extracted data. So, let's start the analysis of the video. The diameter of the disc is 23 centimeters or 0.23 meters. The frame rate of the video is 25 frames per second. So, I've loaded the video in Tracker, but before we can start our analysis, we have to do some setup. First I will select the frames that I want to use in the analysis. I'll forward the frame until the disc is released. So from that point, we expect the disc to move at constant velocity. Continue to the end point. Here. So, and then we have a look at the clip settings, and we'll see it's 33 frames, and I do not want to click 33 times, so I will do that every 3 frames. Frame rate 25 frames per second, which is okay, so that's fine. So we move the disc back, and now we look at the calibration of the distance. We'll see here the blue measuring tape indicating 1 meter, which is not correct. And I've measured the disc being 23 centimeters, so I'll position the tape to the disc, and we have to indicate that it's 23 centimeters. Okay, it's indicated properly. You have to be careful about that. I'll hide the measuring tape, and we have a look at the coordinate axis. It starts here. Basically, we want to start our measurements. The position we will click right here in the middle of the disc. Okay, so hide the coordinate axis, and basically we will have all steps of our trail, and we have an indicator so we can start following. Okay, let's have a look. That's the first one. So, we're ready. Not a bad job. Almost lined up along a straight line. So we'll have a look at whether we can do something with the analysis. And we have here best fit line, indicating basically an A parameter of 0.693, which, if we look at the formula, should be our velocity. Let's have a look at that. So, before we can start modeling, we need some information from the tracker. We need the delta t information, so we can see here that is 0.12 seconds, and we need to calculate the initial speed. So we need also to be able to see delta x in the first 0.12 seconds. And we need the end time, 1.2 seconds. To calculate the initial velocity, we need the information from tracker. Here you can see the first two records of our experiment. We calculate the initial velocity with the change in position over the change in time, giving us an initial velocity of 0.72 meters per second. We need this information in our model, so let's have a look. So, let's have a look at the model. First we have to initialize some of the variables. The mass of the ball, the starting position, the initial velocity, which we calculated, the starting time, and the time increments. Also, I've commented out the output file options, resulting in a ball1.csv. In the main loop, the program cycles each time, incrementing the time with 0.12 seconds and recalculating the position of the ball. Also the ball velocity, but since the net force has been set to 0, the ball velocity remains constant. I had to change some things in the basic program. The order for the recalculation and the printing I changed. First printing and then recalculation, because basically my first points were not printed out originally. Also, I changed the decimal delimiter to comma and the output file delimiter to semicolon. The latter was done to facilitate the import in the spreadsheet. Let's check if the model runs. That looks okay. Let's check out the spreadsheet. Let's compare the output of the model with the data of the experiment. I imported the CSV file from the model and the two columns from the experiment. And I created the diagram. In the diagram, you can see the line representing the model data and the circles the experimental data, and we indeed see an excellent fit, indicating that indeed the soccer disc coasted with constant velocity.